Good morning to everyone. As just mentioned by our dean, my name is Francesco De Mola, and my PhD activities have been focused on models and solutions to support urban security and healthcare provisioning, exploiting pervasive and agent-oriented technologies. My tutor is Professor Giacomo Cabri, and my co-tutor, Professor Letizia Leonardi. In these 3 years, healthcare provisioning has been explored at a different level, from general urban security, dealing with ambient intelligence, to the narrower mission-critical context of the territorial and medical emergencies, and finally focusing on the specific aspect of resource management inside and outside the hospital. So let's start from the most general field, urban security. I was involved in the LAICA Project, Laboratory of Ambient Intelligence for a Friendly City, exploiting ambient intelligence techniques for urban security and remote control in Reggio Emilia. The main objectives of LAICA are monitoring humans and vehicles moving in the city, controlling such flows of humans and vehicles with suitable reactions, for example activating traffic lights, and ensuring security, recognizing possible dangerous situations. Here is a global vision of the LAICA components. A set of sensors are scattered all over the city, linked together by a middleware, distributed middleware, able to collect the data produced by the sensor and store them into a central node with the LAICA database. The police headquarters can access this information at surveillance and security purposes, and on the other side you can see also citizens and public monitors that can display information through the internet by means of the mediation of a web server. Here is the map of the city of Reggio Emilia with the small pictures representing the sensors installed in the different locations of the city. And for each sensor there is an agent belonging to the agent-based middleware. So we can see the agent for the park, the traffic lights, the subway, the database agent, and so on. These agents can communicate each other by means of the lower layers of the agent-based distributed middleware I have implemented in Jade on top of the Jade platform, and it acts as a mediator in component interactions. In fact, we can see that the software of each sensor can communicate at a high level, sending information to the operating central, exploiting the underlying layers built on the top of the multi-agent platform. So we have the peripheral component and the centralized component. Now just a glance to the architectural schema of this middleware. We can only recognize 2 different input interfaces, one for commands and queries to control the components of the middleware, and the other one for data acquisition from sensors, and 2 output interfaces for resulting data and commands, and to store permanent data on the database. In particular, the already mentioned centralized component is in charge of lookup and monitoring the other components and coordinating the remote data sources, and on the other side the peripheral component wrapping each data source, composed of the input filter and the data collector that are modules in charge of acquire data from the sensors. Then the event generator can implement the conversion logic of data and integrates this data, producing warnings and events. These objects can then be pushed to the event channel and delivered to the other components of the middleware. Here is a deployment example in the central park of Reggio Emilia, where some cameras have been installed, and the related agents can acquire information from these cameras and can send the event message to the components, the other agents running in the main container in the centralized node, exploiting the LAICA multi-agent platform built on the top of Jade. And for example, here we can see the database agent storing information received by the other agents, in this case the camera of the park, into the LAICA database. And here is the user interface of the Jade main control panel, where we can see the list of the agents executing in each distributed location of the city, in each agent in its own container. So let's pass to the most mission critical domain of medical emergencies. Why mission critical domain? Territorial emergencies have some important features about that are distribution, dynamism, mobility, and unpredictability. And we can talk about a mission critical domain because of the requirements of reliability, flexibility, context awareness, reactivity, and real time in the communications. And last but not least, we have also high heterogeneity in medical devices and involved actors and organizations during emergency operations. In fact, also in a small scenario, we can see that a lot of people belonging to different organizations are involved. For example, volunteers, medical staff, other practitioners, firefighters, and so on. UBMedic is a framework I have deployed and designed to support medical emergencies. It is an agent-based framework built on the top of Jade Leap, providing some facilities, some management facilities and distributed services to support distributed applications with these strict requirements. The context management provides context awareness, and data acquisition and integration of remote medical devices are provided by means of mobile agents. In particular, we can see at the acquisition level, the lowest one, the physical resource interface agent is directly connected with the physical resource, the medical device, and can acquire data from it. Then at the middle level, the processing level, a proxy agent implements the intelligent part of the data processing. It can choose the most performing communication link, implements other advanced diagnostic capabilities, and thanks to mobility can provide portability on small devices and disconnected operations. It acts as a mediator between the physical resource interface agent and the user interface agent that works at the presentation level. So the user interface agent is in charge to display, to provide information to the final user connected with the user device. The UBMedic framework has been enriched with the role system infrastructure that implements some facilities to support, to manage the concept of role with agents. A role adds new capabilities to an agent according to the actual situation where he is executing. So the goal is encapsulating specific medical device handling within roles, separating concerns, separating the business logic embodied into the agent from the interaction logic implemented only inside the role. So, composing UBMedic and the role system, we can obtain the UBMedic Red, that is role-enabled devices, where each device should be equipped with a vendor-specific role. Then, when this role is assumed by the generic physical resource interface agent of UBMedic, he can also acquire the possibility to interact with the specific device. But we can see how it works. When a new medical device joins the platform, it sends a request for registration to UBMedic centralized services. Here, a new generic UBMedic physical resource interface agent is created from the UBMedic central code repository, and then it moves to the requesting node, and here it can assume the vendor's role, resulting in a complete customized physical resource interface agent, able to communicate with the specific medical devices by means of the proprietary protocols, acquiring data from it, and communicate with the other agents in the platform by means of standard protocols, for example, the agent communication language provided by FIPA in Jade. So in this way, this framework can face heterogeneity of medical devices due not only to different domains of acquired data, but also to commercial issues, and also all the consequent integration troubles about incompatibility among devices and dependence on the companies providing them. The UBMedic RED solution is a prototype, a working prototype, that allow heterogeneous devices communicate each other without any a priori configuration and without any a priori knowledge of the specific protocols of the medical device in a sort of plug-and-play installation, because the specific information about the protocols are embodied into the role that should be provided together with the medical device. This prototype has been tested in a local network, exploiting some data produced by some software simulators, producing different medical clinical data in different formats. So let's focus on the specific issue of resource management. The main objective of the research, supported by Eurosoft Informatica Medica in Modena, is to improve efficiency of healthcare provisioning, starting from the context of Italian national healthcare system, where a strong local autonomy in healthcare administration caused wider heterogeneity in the organizational and the information solutions adopted by regions and different local health units. Of course, interoperability is a big problem. In current working environment, different COOP systems are used by the local areas. COOP is a software, is a system where people can ask for visits and treatments, reservations. It is the unified booking center in Italian healthcare system. Some regional projects has been studied, promoting interoperability among different COOPs used in the main region of North Italy. And here are some of the studied architectural diagrams of these projects. For example, the IS project in Veneto, the Upper COOP in Piemonte, and another version of Upper COOP in Toscana, and the SIS project in Lombardia, and finally the integrator COOP in Emilia-Romagna. From the previous schemas, we can deduce a general model of a hierarchical upper COOP, where the local COOP can be integrated at a different level, at a different step of a different hierarchical step. So from the local unit COOPs to the macro area upper COOP, regional and maybe interregional upper COOP. In this context, a new proposal for a model improving healthcare efficiency has been proposed based on the concept of integrated clinical pathways that are multidisciplinary, locally agreed, evidence-based plans describing the expected progress of a specific patient group. In other words, ICPs implement clinical procedures promoting best practice and continuity in the treatment of the patient, and the coordination among different practitioners involved in the treatment of the patients. ICPs can be modeled with a sort of temporal diagrams, like flow charts, composed by different steps connected to several activities and the related transition condition. The model of ICP management is based on two logical levels. The template one, a priori defined by the administration, by the healthcare headquarters, suggesting the best practice for each kind of treatment. And the instance level, where people that where practitioners, medical practitioners, can create a new pathway for the specific patient and can customize the activities and the different steps starting from the best practice described in the template level. Designing a model for actors' role is very difficult because of the number of different actors involved in the treatment of the same patient. So a trivalent model has been proposed where an actor role is completely defined by the identification of the authorization about which entities among the ones composing the temporal diagram of the pathway and the whole pathways or the single steps of the pathway related to which specialties, usually the same specialties of the caregivers, and also the patient, about the patient, so authorizations about the pathways, the real pathways connected, related to the specific patient a caregiver looks after. And finally, a workflow engine operatively manages the pathways, and this engine is composed of an event collector that collects all external trigger events and updates as a consequence the internal status of currently open pathways. Then a monitoring unit continuously monitors the internal status of the pathways, identifying the possible changes that require suitable reactions. It also implements a scheduler to make the pathway timeline go on. And at the top of this stack, the notification dispatcher is an event linker in charge of delivering the information about the changes in the status, in the internal status of the pathways, to the interested actors and maybe also other software standalone systems and so on. A first demonstrative tool has been developed to start a discussion with the final users about the feasibility of this approach and the usability of the designed user interfaces. And here are some screenshots of this tool and the list of the exploited technologies. So let's go to conclusions. In these 3 years, the general domain of healthcare has been explored by means of 3 contexts, summarizing urban security, emergency situations, and resource management in healthcare. Some common features have been identified, the requirements of distribution, dynamism, and coordination. And for most of these fields, agent technology has been proposed to develop some solutions and to implement 3 concrete prototypes for each one of the main fields that are the LAICA Ambient Intelligence Middleware, UBMedicRed for medical device integration, and the ICP Management Tool. After a first evaluation of feasibility and usability of the proposed solutions and prototypes, the big open issue is, okay, technological feasibility, but what about organizational and political matters? Well, a lot of work should be done by institutions to improve their organizational structures in such a way that the adoption of these technologies can produce real advantages. So that's all. I thank you for your kind attention. Here are some of my scientific publications and some other organizational activities I've carried out in these 3 years. Thank you again.